first, I would like to thank the organizers for putting together this wonderful program and for the invitation. So these are my collaborators from the University of Minnesota, Andrei Trubukov, who gave a wonderful talk this morning, and Zheng Wang and Rafael Fernandez. And this talk is based on these two works we put on ICAP recently. So I will talk about Pseudogap. So first, let me give a short introduction of what do we mean, what are the features of Pseudogap we are interested in. So it has been seen in various correlated electron systems, such as cuprates, iron-based superconductors, heavy fermion systems, and recently twisted bilayer systems. And let me use the schematic phase diagram of cuprates as an example for the illustration. So it's one of the clear signature of Pseudogap can be seen by looking at the electron spectral function at the hotspots. So if we look at the normal metal, we know that the spectral function is peaked at the 0 frequency. And if we look at the spectral function inside some ordered state, say the superconductivity or antiferromagnets, the spectral function as a spot is peaked at finite energy, and this gap is set by the mean field order parameter. And the gap, which are highlighted in the pink region that span over a large temperature and doping, is in the state where there is no long-range order. However, if we look at the spectral function, it's the maximum at finite energy. And our goal is to understand the origin of the Pseudogap. And there have been many proposals for the Pseudogap phenomena. Here, we want to start from something very simple, namely ask whether the magnetic thermal fluctuations near the SDW ordered state can give rise to Pseudogap behavior. And there have been several supportive evidence of this scenario. For example, in the numerical DMFT study, people have found that the anti-short, so among various interaction channels, the antiferromagnetic spin fluctuations dominate for the Hubbard model at half-filling. And also, one can show that actually the static fluctuation dominate over the dynamical fluctuations. So this gave us some confidence that the static thermal fluctuations might play a role of the Pseudogap behavior. And also there have been experimental evidences back in like 2 decades ago that show the collective short-range magnetic fluctuations are indeed present in the phase diagram. And so in our work, it turns out that within this scenario, we can do an analytically controlled calculation, and we can study many things in a great detail. And of course, we are not the first person thinking about the magnetic thermal fluctuation scenarios, and there have been several people thinking about it. And our recent study revisiting this problem are motivated by several progresses in the last few years in this field, in particular in numerics. So let me walk you through the motivations of our study. So first, there have been new quantitative understanding from numerics from the weak coupling to intermediate coupling regime using DMFT and diagrammatic Monte Carlo. So in this very nice work led by Anton, they studied the Hubbard model at half-filling with nearest neighbor hopping. And they found this is a schematic, this is a phase diagram they obtained, which shows that because it's only nearest neighbor hopping at half-filling, the Fermi surface is actually perfect nested. As a result, one only need an infinitesimal Hubbard interaction U to induce the antiferromagnetic order. And in this purple region, they found Pseudogap behavior and it shows that it doesn't depend on temperature significantly, and this is also consistent with experiments. And to understand the temperature-independent pseudogap behavior, even at weak and intermediate coupling, there are proposals. They proposed to this weak coupling scenario, which have been discussed in the literature in the past. So the argument basically is that if one do a one-loop calculation, considering only thermal fluctuations, one can show that the pseudogap scale is proportional. It scales with temperature times log of spin correlation length. And one might ask, so to understand how this pseudogap scale depend on temperature, one need to understand how the correlation lengths depend on temperature. So as we are working on a one-loop theory, one might think that within one loop, one can compute the spin the psi and find that it's temperature independent. And as a result, the pseudogap scale should be strongly temperature dependent. However, numerically, they found that actually the spin correlation length has a Heisenberg behavior, namely that it scales with exponentially with 1/t. So that as a result, it diverges at a low temperature. And if you plug this psi into this form, you will find that the pseudogap is independent on temperature, which is consistent with the numerical observations. However, it is not quite consistent. On the one hand, one starts from a Fermi liquid in one loop theory to obtain the pseudogap scale, and on the other hand, to obtain the psi, one need to evoke like a high non-perturbative higher order processes. So in our minimal model, we want to show that the one loop is not enough near the nil temperature, and instead one need to go to infinite series consistently. And a second motivation for our study is some problem free Monte Carlo study of the spin fermion model, like say studied by Aries, and they found that interestingly in this spin fermion model, both the spin density they found from this spin fermion model they can show both the spin density wave and the D wave superconductivity. And furthermore, they show the evidence of pseudogap behavior that is only seen above the SDW and the superconductivity ground state, but it cannot be seen above a paramagnetic ground state. So we want to understand this better from our minimal model and identify the range of the magnetic pseudogap. And a third motivation is to ask a general question. Is pseudogap in the precursor scenario a generic property near an ordered state? The short answer is it is not necessarily true. For example, it has been known for quite a while that in 1D charge density wave case, while there are fluctuations, however, they doesn't give rise to pseudogap behavior. And it turns out it depends on the delicate kinematics of how the electrons scatter with the collective excitations. And so in our work, we want to better understand these kinematics, and we show that there is a crucial role played by vertex diagrams for the pseudogap, and it would also be helpful for one to understand or design their physical models that can control the strength of the pseudogap behavior. So with this introductions, let me introduce the model we considered and the methods applied in our study. So we consider a very simple band Hubbard model on a square lattice with both nearest neighbor and next nearest neighbor hopping. And this is a Fermi surface like in the blue contour. And we want to study the Hubbard U to 2 electron volts, which is about 7th times the Hopkin strength. So we are going from the weak to intermediate coupling. So we know that as we tune the doping closer to the half filling or increase the Hubbard U, the system will will transform from a normal Fermi liquid to the SDW ordered state. And for simplicity, we will just consider the SDW order at momentum pi, which is this antiferromagnetic order. So first, let's look at the mean field picture, how the spectral function behaves. I already mentioned that. Let's look at the hotspots and as the SDW order onsets, this large Fermi surface will split into small and large electron and hole pockets, and these hotspots are gapped. So at high temperature, we would say expect the spectral function to be peaked at 0 frequency, and at low temperature, it is gapped with a gap set by the SDW order. And however, this mean field picture breaks down near the nil temperature. And now let's say what we should expect. So as the temperature increases from the SDW order state closer to the nil temperature, we expect to see two gap features. The first one is a small gap set by the mean field SDW order, and the larger one is which we call a hump, is another gap scale exactly which is a pseudo gap I refer to. And at a nil temperature, this SDW gap vanishes, and we can only see this hump feature. And as temperature further increases, there will be more spectral weight filling in at a lower frequency, but we can still see this maximum at finite energy. And it is only when we go to a much higher temperature, the spectral function recovers to the normal Fermi liquid behavior. So our goal is to in our work, we want to study the interplay between the SDW order data, the pseudo gap energy, as well as the characteristic energy for the fermions, which is VF times the inverse correlation length as temperature varies. And this can give us, this can resolve two puzzles. First, is how to understand the temperature independent pseudo gap above the nil temperature while we start from a Fermi liquid theory. And the second puzzle we want to question we want to address is to pin down the range of the magnetic pseudo gap in the Hubbard model. Okay, so actually one can understand the magnetic pseudo gap from thermal fluctuations in a very simple picture. So the intuition is that at finite temperature, the electron wave packet, namely is the de Broglie wavelength, which is VF times the inverse temperature. And if this de Broglie wavelength is much smaller than the spin correlation length, it effectively sees the system as in a long-range ordered state. As a result, we should expect to see the pseudo gap as in the SDW ordered state. However, this criteria this picture will put a very strong constraint on when pseudo gap happens. And I will show later that actually this criteria, we can relax this criteria from our study. So mathematically, what one do at one loop order is to simply compute the self-energy of the fermions interacting with the paramagnons at 0 Massubaro frequency, and this is a result when obtained, and that has been known for quite a while. And when the self-energy is greater than the frequency, one would expect to see the pseudo gap behavior. And this immediately tells us that when the dimensionless thermal coupling lambda defined here is greater than a threshold value, which is of order 1, the system shows a pseudogap behavior, as you can see from this picture. And in particular, when lambda is large, the pseudogap is larger. And we found that, and then one can show that when in this limit, it is enough to pull the fermion-Green's function out of the calculation and obtain the self-energy at only the by only integrating out the spatial fluctuation of the boson. And as we know from the Mermin-Wigner theorem, in 2D, this spatial fluctuation will give a logarithm, and this is exactly where this log psi comes from. And this is a form of the self-energy, and you can see that it takes the same form as a SDW self-energy as when you identify the gap with the root of T log psi. So from this one loop theory, one can already obtain the pseudogap behavior, and following a similar logic, one can obtain the pseudogap behavior from thermal fluctuations in the SDW order state. However, because there is a log, it turns out that there is no small parameter to justify why one only consider a one loop calculation. Actually, it is important to consider higher order diagrams. So what we do is to self-consistently determine the Green's function and the spin correlation length by summation over all loop orders with a leading logarithmical accuracy. I will skip the details of how we do it, but I would be happy to chat about it after the talk if you are interested in. And with this procedure, we can solve self-consistently the SDW order data and the chemical potential below the nail temperature, and the spin correlation length and the chemical potential above the SDW order. And I want to emphasize that there is not an RPA or Ashbrook type summation, but it can be done quite accurately if we restrict to thermal fluctuations. So now let me discuss the results. So this is the result we studied when U is 1 electron volt. And let me walk you through how the data, the SDW order, the pseudogap energy, and the characteristic fermion energy evolves as temperature increases. So deep in the SDW ordered state, we can only see this gap's SDW gap. The spectral function is peaked as a mean field case. And as temperature further increases, you will see the two gap scale emerges, and this explains the pseudo gap scale and also the gap of the SDW state. And as temperature further increases, the SDW gap vanishes above the nail temperature, and we will only see the pseudo gap scale. And when frequency is smaller than the characteristic fermion energy, there will be spectral function filling in this gap, this minimum. And importantly, you can show that the pseudo gap scale from this study that doesn't depend much on temperature. And this is a consequence of summing over the infinite series, and we denote this feature as a strong pseudo gap behavior. And as temperature further increases, the system should recover to the normal Fermi liquids. But before that happens, it needs to shrink. The gap needs to shrink. The reason is because here, it turns out the infinite series summation breaks down. However, as the effective thermal coupling is still above the threshold value, but it decreases with temperature, we can show that it's enough to just consider the one loop analysis I considered at the beginning, and show that this pseudo gap actually strongly depends on temperature, and eventually vanishes at higher temperature. So this is how it evolves, and I want to emphasize again that this strong pseudogap behavior is a consequence of the fact that the spin correlation length depends exponentially on inverse temperature. And this is also consistent with the numerical studies done by Anton et al. And from that, we immediately recover the temperature independent pseudogap behavior. And another comment I want to make is that we can compare how the spin correlation length and this fermion characteristic fermion energy with the temperature, and we found that in most region of the pseudogap we found, it actually fits in the regime where the de Broglie wavelength is greater than the spin correlation length. But nevertheless, we can see this pseudogap behavior. And so the next I want to discuss about the phase diagram from our study. So previously I have talked about the thermal fluctuation scenarios. However, if we want to understand the phase diagram broadly, it's important to consider this critical boson near the SDW quantum criticality, which include a Landau damping term. And we found that by comparing the Landau damping term with the spin correlation length, there are two regimes. Near the SDW ordered phase is the thermal fluctuation dominated, and away from it is quantum fluctuation dominated. And we can set a crossover temperature between these two regimes. And we can further show that this crossover temperature TQ is comparable to the pseudogap scale. This gives us the confidence that it's enough to use this thermal calculation results to set a boundary for the pseudogap behavior. And in particular, we look closely at what happens at right above the quantum critical point. And we found that the thermal coupling lambda here is a constant in temperature, and also it's below the critical lambda, which means that there is no pseudogap right above the quantum critical point. Of course, these are calculations results by numbers, so it might change depending on the model. And to summarize, so this is a schematic phase diagram we obtained. So in this thermal regime, there are both strong and weak pseudogap behavior. And in this strong pseudogap region, I show that we can use these infinite summations and find that the pseudogap scale is comparable to Hubbard U and it's temperature independent. And in this weak pseudogap regime, we can use a one loop calculation and find that it's strongly temperature dependent and vanishes above a crossover temperature TP. And in both calculations, we didn't use any self-consistent one loop. Actually, one can show that the self-consistent one loop doesn't give rise to pseudogap behavior. So the question is how to see the connections between these different methods. So to understand that, we go back to the literature and look for cases when there is no pseudogap behavior. So one case is a self-consistent one loop, as I mentioned earlier, and another is a special kinematics that gives a special combinatorics. And and for both cases, one can it turns out somehow it's convenient to understand them using this continued fraction representation, where what is important is the structure of these kappa factors. And it turns out for both cases, so this is a plot for the kappa factors, which for both cases, they fall into a straight line. Then we found that there is a set of boundary or models when the kappa is on the straight line. And for these models, there is no pseudogap behavior. And for models when the kappa of all the integers are above this straight line, we find it shows pseudogap behavior. And for the models when kappa is below or on the straight line, it doesn't show pseudogap behavior. And to understand this structure better, we further write down the thermal self-energy as a convolution of the Fulgran's function and the vertex function. And what is important is the behavior of the vertex function. And we show that for the non-pseudogap cases, the vertex function doesn't depend on frequency significantly. And in particular, for the self-consistent one-loop result, it is the real part is a constant in frequency and the imaginary part vanishes. However, for the cases with pseudogap, we find that at a low frequency, the imaginary part of the vertex function becomes important and diverges. And we think this feature is important to understand the pseudogap and to also demonstrate the crucial role of the vertex corrections. And it is also consistent with recent numerical studies using DMFT. And this is a summary of my talk. I introduced and studied a minimal analytical model to capture the thermal evolution of pseudogap behavior, and we found agreement with various numerical studies. Thank you.